Abnormalities of cardiac rhythm, arrhythmias, may compromise cardiac output or induce cardiac ischemia. Appropriate treatment of an arrhythmia depends on accurate diagnosis of the type of rhythm disturbance present. Before we go on to discuss arrhythmia diagnosis, we need to briefly revise some relevant principles from cardiac physiology. We will focus in on the SA node at the cellular level to illustrate these principles. As demonstrated by the cell center field, all cells of the cardiac conducting system and myocardium maintain a gradient of electrical charge across their membranes, with the extracellular fluid demonstrating a positive charge relative to the intracellular compartment. This polarization of the cell membrane is an energy-dependent process. However, as shown here, virtually all electrically active cells in the heart have the capacity to spontaneously and rhythmically open ion channels in the cell membrane, with consequent equalization of charge. This capacity to periodically depolarize their membrane in the absence of an external stimulus is termed automaticity. As the membrane spontaneously depolarizes, a threshold is reached and an action potential is generated, which propagates out to surrounding cells, ultimately triggering depolarization of their membranes. In this way, once one region depolarizes, a wave of depolarization spreading through the entire organ is generated. Within the myocardium, depolarization spreads from cell to cell at a rate of approximately 0.5 meters per second. However, within the components of the ventricular conducting system, the velocity of conduction of depolarization is more rapid, between 4 and 8 times higher than that of muscle. This difference in conduction velocities between myocardium and the specialized ventricular conducting system is central to understanding the ECG analysis of arrhythmias. Cellular depolarization in conducting tissue and myocytes is followed by a slower phase of repolarization, and during much of the latter process the cell is refractory to further stimuli. During this refractory period, the cell will not depolarize either spontaneously or in response to an external stimulus. Cellular automaticity and the existence of the refractory period are crucial to understanding cardiac arrhythmias. The cells of the SA node have the highest rate of periodic depolarization, and therefore under normal circumstances the SA node drives the heart rate. However, if the SA node is damaged, other foci within the conducting system or myocardium can take over pacemaker function and drive cardiac depolarization. As one moves further down the conducting system away from the SA node, the automaticity of these latent pacemakers decline, and the heart rate generated by them will tend to be lower. When studying the videos in this section, it is very important that you are clear about one thing. In this section, section 4, we will only deal with the ECG diagnosis of arrhythmias in the presence of an intact ventricular conducting system. The diagnosis of arrhythmias in the presence of altered cardiac conduction is more challenging and must wait until section 5.